Today, we're going to show you how to optimize a SelectIO for optimal signal integrity using the Xilinx UltraScale FPGAs. With the SelectIO now operating at multi-gigabit data rates, designers require next-generation technologies to ensure excellent operating margins. Equalization, typically reserved for high-speed transceivers, is now available for all SelectIO of the UltraScale FPGAs. Every SelectIO of the UltraScale FPGA features both transmit preemphasis and receiver CTLE, or continuous time linear equalization, to compensate for signal degradation and thereby ensuring optimal link margin.
Let's explain what we mean by signal degradation. When a signal travels through a channel such as a package or baud trace, the high frequency harmonics are attenuated more than the low frequency harmonics. This can be due to both the conductor loss and dielectric loss and results in intersymbol interference or ISI. Multiple techniques like transmit preemphasis and receiver equalization have been used in the industry to compensate for these losses, particularly in high-speed serial links. Now, the SelectIO in UltraScale FPGAs feature both transmit preemphasis and receiver CTLE. CTLE functions as a high-pass filter that is designed into the receiver circuit to compensate for the low-pass behavior of the channel. When selecting a CTLE gain setting to compensate for the channel loss, it is important to ensure that the peak of the CTLE frequency response is at the optimal frequency and gain setting. The CTLE has 5 different gain settings to optimize the receiver eye opening. For example, a user can vary the gain from 0 to 3 dB in steps of 0.75 dB when implementing a DDR4 interface using a Pod 1.2 IO standard. Similarly, a user can vary the gain from 0 to 6 dB in steps of 1.5 dB when implementing the LVDS IO standard.
Now, let's see the CTLE in action. We have an Agilent Jaybird scope producing a 2.4 gigabit per second PRBS 15 data pattern driving a 16-inch trace over FR4 connected to the Kintex UltraScale device on our characterization board. The total loss in this path is 6 dB. Then, using a very simple input-output circuit, we have a Pod 1.2 output driver driving into the 32 GHz Agilent Infinium DSA-X scope. Displayed on the DSA are 4 eye diagrams with different CTLE gain settings. The eye diagram at the top is with the CTLE turned off, followed by eye diagrams with 3, 4.5, and 6 dB CTLE gain settings respectively. We see the best eye opening with the gain setting of 6 dB. The total jitter has been reduced by an astounding 50% when compared to the eye diagram with the CTLE turned off. So for this example, we see the best link margin at a gain setting of 6 dB.
That is exactly right. That is why Xilinx provides simulation models where you can incorporate the CTLE model in your standard SI analysis and determine the optimal gain setting before you design your board. Now let's walk through the process.
What we have here is an Agilent Advanced Design System, or ADS workspace, with a few simple simulation schematics. The first one gives you the frequency response of the various CTLE gain settings. The second one allows you to generate a time domain response and plot an eye diagram at the CTLE output. The schematic consists of a PRBS 15 source, a PCB trace model, and an UltraScale IBIS 5.0 receiver model for the Pod 1.2 receiver with the CTLE IBIS ISS model. the same simulations can be set up in other commercially available EDA tools. You can see from the simulation results that selecting the appropriate CTLE gain settings generates a larger eye opening than when the CTLE is disabled. You can cycle through the various CTLE gain settings in your simulation to optimize the eye opening for your specific channel characteristics. Today, we have shown you how to use the UltraScale SelectIO CTLE capability to optimize the DDR4 link margin. We also showed you how to simulate the impact of CTLE on your system before designing your printed circuit board. Collectively, this methodology will ensure excellent operating margin when designing high-speed interfaces like DDR4. For more information, please visit us at Xilinx.com.